In this video, we're going to be taking a look at a velocity versus time graph. We are going to be analyzing each section of the graph to see what type of motion is going on in each of the segments. We're going to take a look at what the acceleration is and then also the displacement. So let's start with this first section over here. It's going at -3 meters per second. Because it's a flat line and has no slope, it stays right at -3, which means it's moving back in the other direction at 3 meters per second. This would be a negative constant velocity. For this portion up here, because it's above the x-axis, it looks like it's at about 2. This has a positive constant velocity. And anytime where you have some kind of slope, that means you're definitely accelerating because your velocity is changing. This one is heading back towards 0, which means it's definitely slowing down. But it's still going in the positive direction because all of these values are above the x-axis. And then this one right on 0 is definitely going to be at rest. So if you're taking a look at the line, if it's flat, that means it's going at a constant velocity. If it's flat and on the x-axis, that is the only case where it is at rest, going at 0 meters per second. And the next segment over here is going to be moving up. So this one is definitely speeding up. And it's speeding up in the positive direction. Now, just because it's slanted up doesn't mean it's speeding up. The way that you know that it's speeding up is if it's moving away from the x-axis. If it's moving away from 0, then that means it's increasing the rate that it's moving. This one is slanting down back towards 0, so this one is slowing down. And this one is still going in the positive direction. So that means it's still moving forward, but the rate that it's moving forward is decreasing. And then now here, as I said before, if we have a line that's moving away from the x-axis, that definitely means it's speeding up. Except this one is speeding up in the negative direction. So oftentimes when people see a negative slope, they automatically assume that it's slowing down. But because this one is moving away from the x-axis and away from 0, that means it's increasing its negative velocity, which means it's going faster and faster in the negative direction. Now, the second thing we're going to take a look at is we're going to go ahead and solve for the accelerations. So if you solve for any slope, it would be y2 minus y1 over x2 minus x1. And that would equal the slope, which is the acceleration. And we know that's the acceleration because the slope is finding a rate, and the rate at which velocity changes per time is the acceleration. So these first two sections do not have a slope. They are completely flat. So they are both at 0 meters per second squared. That doesn't give any indication of how fast they're going, but how much they're increasing or decreasing their velocity, which is not at all. Now this portion over here, if we're going to take our y2 minus y1, it ends at 0 meters per second. So we have 0 minus, and it started at 2, so minus 2 meters per second. And then we're going to take our x2, which is 10 seconds, minus our x1, which is 8 seconds. And then we get -2 meters per second over 2 seconds, which is equal to -1 meters per second squared. So I'm going to go ahead and slide that in right over here. For this flat portion over here, and especially because it's at rest, this one does not have any acceleration, so 0 meters per second squared for this portion. Over here, we have a positive acceleration. It looks like it's rising up 5 in 2 seconds from 14 to 16. So technically it would be 5 minus 0 over 16 minus 14. And then you get 5 over 2. And then you would get a final answer of 2.5 meters per second squared for this portion over here. Now for our last section, we have a constant slope here, although it's going from the positive down below to the negative region, because the slope stays constant, that all has the same acceleration. So we can go ahead and find the acceleration for the entire thing, which goes from a 5 all the way down to negative 5. So this is our y2 value, negative 5, minus our y1, which is positive 5. And then that goes from 16 to 18 seconds. So 18 minus 16 seconds, that gives us negative 10 divided by 2, which is negative 5 meters per second squared. All right, so we got all of our accelerations for each of the different sections. The last thing we're going to do is we're going to find the delta x. A lot of times people say the delta x is the area underneath the curve. I don't particularly like that, because if the curve or the line is below the x-axis, then it's actually the area above it. So it's the area between my purple line and the x-axis. So if we close this section off and then make it into a little rectangle, the velocity would be the height of the rectangle, and then the width would be the time. When you take that velocity times time, that will give you the delta x. So we have negative 3 down and then 3 over. So we have negative 9 meters. For this section over here, let's go ahead and close this off. We go from 3 to 8, which is 5, and it goes up to 5 times 2 is 10. So now it goes forward 10 meters. Then we're going to take a look at this little right triangle here, which is 1/2 base times height. 1/2 times the base is 2 from 8 to 10. So 1/2 times 2 is 1. And then 1 times the height of it is 2. So it's going to be 2 meters. And then for this section over here, we're going to break it up into 3 right triangles. We're going to cut it right over here and right over here. This one goes over 2, and then it goes up 5. So then 2 times 5 is 10, times that 1/2, because it's 1/2 base times height. So it goes forward 5 meters. And then our final section, we have a width of 1, and it goes up 5. 1 times 5 plus that, or excuse me, times that 1/2, because it's 1/2 base times height. This is 2.5. And this final section is basically the same thing, except flipped in the negative direction. So 2 times negative 5. 1 times negative 5, because from 17 to 18 is 1. 1 times negative 5 is negative 5, and then times that 1/2, because it's 1/2 base times height, so that's negative 2.5. All right, so we found areas for all of these little sections of this rectangle, this rectangle, this right triangle, this right triangle, and then these last two as well. And let's go ahead and sum these up so to get a final total delta x. So the negative 2.5 and 2.5 are going to cancel each other out. So we have 5 plus 2, which is 7, 7 plus 10, which is 17, minus 9 down over here, which is then 8. It has a final delta x of 8 meters. So to sum things up, when you're analyzing a velocity versus time graph, if you have flat lines such as these, they are definitely going at constant velocity. If it was something at rest, then it would be right on the x-axis to show that it's going 0 meters per second. If you have a certain slope, anything that is slanted away from the x-axis is speeding up. Anything is slanting towards the x-axis is slowing down. And then when you go ahead and find the slopes using this formula right here, then you get those exact values. If you want the delta x's, the displacements for each of the different segments, you're going to find the area of some sort of rectangle, square, or triangle. And then you can go ahead and add those up if you want a total delta x. So I hope that was helpful to you. Thank you for watching and listening.